My name is Thai Pham. I'm working at the FemtoMAX group. I'm in my macro laboratory. Today I'll talk about more technical stuff that we have been developing X-ray absorption spectroscopy at FemtoMAX, and we have been commissioning some experiments. And today I'll present with you some of the results that we got from this ultrafast X-ray absorption spectroscopy. Just briefly about the X-ray absorption spectroscopy. So when X-ray absorptions, mainly we measure the absorptions of the sample at the X-ray domain. So what we do is that we measure the absorptions and we tune the monochromatic X-ray energy on the sample, and we measure the absorption sample. How do you have a laser?
It's a top button.
Top button. Okay. So when we tune the energy of the sample, we apparently excite the electron from the core level of the atom into the higher level, and then in the absorption we will start to see the absorption peak at the pre-etch level here, and then when we tune it further up in the energy, then we start to have the energy, the electron excited to higher level, and at some point it go into the continuum state, and when we have a huge jump in the absorptions. And then when we tune it even further higher in energy, then the electron, here it changes. The electron will go out of the atom, and it's generated photoelectron wave that is scattered by the neighboring atom. And this scattering wave of photoelectrons will come back and interfere with the outgoing photoelectron wave and generate the interference patterns around the absorbing atom. And that results in the modulation of the absorptions. So in the absorption, we can divide into two parts. One part is the same reasons, where the electron, where we have the energy is about 50 eV after the absorption edge, and after that, and the part that is higher than 50 eV after the absorption edge. So this is a very powerful technique that allows us to study the structure of the molecule at the molecular level, and it can be used for any media from liquid, solid, and gas phase. This can give the electronic structures, and it can map out the absorption, the energy level here, and of course it will give us the local structure with very high spatial resolution. And so this is for the static structure, and if we measure the absorption of different time delay for different sample, we can we measure different time delay depending on what coset that we are looking at, and if we have the structure at different time delays, then we have the dynamic of the system, and so we would know how the system works, how it functions. So the principle of the time resolved absorption spectroscopy is based on the stroboscopic technique. So where we optically excite the system with the pulse laser, and at some certain time delay, the X-ray coming in and probe what caused by the laser excitation. And one example of this is that we can have potentially application in studying so-called solar fuel molecular. So in this case, a molecule is composed of chromophore and attached with electron donor or electron acceptor to the side, and it has the reducing or oxidizing catalyst. If we use this technique, we can probe a different site of the molecules, since it's element specific. So it's sensitive to the oxidation states of the atom, so we can actually track out how the charge is transferring within the molecules here. So this can help us to understand how the coset work and optimize the molecules, and have a better application into the solar harvest thing. And of course, it can also be used to study the structure change of the molecules after excitation. So we can study Yantala distortion or flattering of molecules that have been well studied using this technique. So a bit of the history about this technique. This time resolve has been implemented about 20 years ago, start from the synchrotron. So in the synchrotron, when it's operated in the hybrid mode, so in the hybrid mode, the electron pattern, it looked like this case, and the electron is from, we use one single bunch of electrons that is accommodated in a big gap of the other electron. So this can be used for probing the absorption. So in this case, they have been using a femtosecond laser running at 1 kilohertz and excite a sample, and this used to probe the absorption with the IPD. Since lasers running at 1 kilohertz, we can only use one 1 kilohertz or 2 kilohertz for probing the absorption. And most of the X-ray in this case, so even though it's running at 1 megahertz, we wasted the X-ray, most of them. So we use only one of the thousands of electrons. So later on, like 10 years later, they have developed a faster data acquisitions where most of the X-ray here have been used. So in this case, they use a 500 kilohertz laser to excite the sample, and 1 megahertz of the X-ray to probe the absorptions. In this case, the laser running 500 kilohertz, but it is picosecond laser. But since we have picosecond X-ray, so this doesn't matter. It does not change the resolution of the system. And so here they have, since this is megahertz, they have a megahertz data acquisition system, and it's very fast, and the good signal to noise can be reached within a much shorter time scale compared to the kilohertz system here. So when the free electron laser have been emerged, and with the advancement of free electron laser, we have much higher flux, and it had a femtosecond resolution. So this technique has been extended to free electron laser as well. So this is one example of the SACLA when they split a white beam of the free electron laser into two parts. So one part is used for probing the sample, and one part used for reference. So since the free electron laser has a very high stochastic property, so this reference has been very important because it can be used to normalize to get the right absorption, transient absorption spectrum. And so in this case, the one arm is focused on the sample, and then it dispersed by a silicon crystal here, and the other arm is bypass the sample, also dispersed, and they both measure the 2D detector. And they can get the difference. They can get different transient absorption, different time delay quickly. And another case is that they can use the monochromatic beam, where the X-ray it monochromatizes and shoot onto the sample, and then they tune the energy to get the transient spectrum. In this case, they also have to use the I0, which is measuring the incoming X-ray intensity. And it has become very critical. So these both systems have been working, and one typical example of what they have found out is that they have been studying many systems, but I just briefly present one of the prototype system here, which is iron trip pyridine, which heavily studied. So in this system, the iron in the center here, and it's linked to 3 bipyridine ligand around it. So this system is that when it excites, it at the beginning it's at low spin state, and once excited, go into the high spin state. And they have nailed down the mechanism of this process that once excited into the metal to ligand charge transfer, the electron stay for about 150 femtoseconds before populating the high spin state, and then from high spin it goes back into the low spin state at about 600 picoseconds. So with free electron laser, they can get a different different time, and very nice time trace you can see here, this is measured at the LCRF in the US. At the FemtoMAX, we are actually bridging between the free electron laser and the synchrotron. We have femtosecond accurate pulse, and we, even though we are very low in the flux compared to the free electron laser, but we have very stable source and very broad band of accurate. So we can actually tune from 2 kV up to 20 kV, in which the usable accurate for the accurate absorption spectroscopy is from 2 kV to 12 kV, which cover the KH of the fluorine, sulfur, and chlorine, and some 3D transition metal. We also have the femtosecond laser that is tunable for different wavelength for pumping the sample. So this is a setup that we use at the FemtoMAX for measured accurate absorption spectroscopy. So in this case, we have X-ray coming from here, go into the tube here, and the laser sending basically from this side and couple to the X-ray to excite the sample. And in this hole, we have I0 detector measuring the incoming X-ray intensity. And here the real photo of the setup. This is the chamber that we see here that I do. So in the cap, we don't have this APD, the fluorescent APD, but you can see the fluorescent APD from the side to collect the fluorescent that excite from the X-ray. And in the back, we have a transmission APD to measure the transmission of the X-ray. The sample is in the form of liquid, and it's flowing, free flowing jet, and it's circulating with the pump. So one important measurement, one important thing for the accurate absorption is that we need to have very good timestamp. So for this, we are using a so-called ping, and which is based on RF cavity to measure the time jitter between the laser and X-ray. So with this technique, we can precisely measure the arrival time of the laser with respect to the X-ray. So the principle is that we have electrons at Lund. When it passes by an antenna, it generates the electric signal, and the laser measured with the fast photodiodes generate a pulse here, and they go via a bandpass filter and generate a ringing pattern in here. So we have a laser first ringing and the X-ray ringing here. They are both sampling at very high speed, and we can nail down the time which is the space between these two ringing signal. And with this technique, when we apply it into study the coherent optical phonon, we can see the oscillations from the diffractions. And this wiggling, we can nail down that we have the time resolution of about 210 femtosecond. So for how do we acquire the data? So the data, it's the X-ray detected by the APD, and we can see here this is the oscilloscope where we see the X-ray signal, which is the negative pulse here. What we do is just integrate the peak here for this is for different detector, including the I0, the fluorescence, and the transmission detector. So in the data acquisition, the data acquired 10 Hz, and the laser excites the sample at 5 Hz, which is half of the X-ray. So in this case, one X-ray is used for probing, and one X-ray is used for referencing the sample. So the transient absorption for the case of fluorescence, it can be calculated by the intensity of the fluorescence when the system pumps, and subtract for the intensity, the fluorescent intensity when it unpumped, and normalize with the incoming X-ray. So then you can have this one. Then this is the result that we get. This is the transient absorption of iron chip by feeding. This is the PET sample. And you see here, this is the absorptions when the red one is when it excites, and the blue one is when it's unexcited. And the orange curve here is the magnified of the difference between the two spectrums. So when we overlay this transient absorption with the literature, the one that has been already measured, we have perfectly overlap with the literature. And for a given accumulated flux of 1 to the 8 photons per point, we have quite similar signal to noise. And in this case, the total collection time is about 7.5 hours in this case. So this means that we have measures. We got the transient absorption correctly, and for the given flux here, which is similar to the given flux on the literature, our sensitivity is quite good and similar to what has been measured at the synchrotron. So when we look at the time trace, where we tune the time delay, and this is orange circle here, what measures the FemtoMAX, and the black gray circle here measure the free electron laser. We see that we are slower, even though the same system. So this can be explained that since we have very low flux, the measuring time takes much longer than the free electron laser. Since the measuring time is longer, there are more errors involved in the acquisition process, and that could make our time resolutions lower than the free electron laser. And when we plot the time zero for each scan versus the acquisition count, we can see we have the jumping in at the time zero for different scans, and it hints that our timing tools is not really perfect, and we still need to improve it. So in summary, we have successfully measured the transient absorption for ion trip bipyridine, and we also have measured the other routine trip bipyridine, a similar compound. And there are a couple of points that we need to improve to get the better signal to noise and better time resolutions. Here's like we're going to have a better timing tools, and we will have a better detector for to get better signal to noise. Yeah. So yeah, this is what we got. Thank you for attention.